Okay, so we're going to look at the calculus behind parametric equations. And what I'm going to do here is I just made up a pair of parametric equations, I guess. X equals t squared minus 2t and y equals t cubed minus 3t. You go to Desmos. I'm going to start graphing it. I'm starting at -10, and you don't see it yet. T equals -10. It must be off the screen. So I'm going, oh, here we go. Now at round t equals -2.4, here it is. And it's being right there. It looks like we might have a maximum point. It's concave down. That's around t equals -1. And then right here, it made a drastic change. That looks like it's t equals 1. If you look up on the upper left-hand corner, and makes a drastic change. It also looks like for xy coordinates, that was at -1 comma -2. And the maximum looks around 3 comma 2. Now, I haven't really done anything with this. It will all be a surprise to me. But the calculus should be able to show us what's behind all of these qualities of the graph. So let's do the calculus. So the derivatives, the dy dx. Now we've talked about how to do this with a parametric equation. You take dy dt, so the derivative of y with respect to t, over dy or dx dt. And that's the first derivative. Now, according to this derivative, if we factor it, that would be t squared minus 1, so t plus 1, t minus 1, over 2 times t minus 1. Oh, we have this big cancellation we can expect, so I don't really want to look at the cancellation because those are important points that I'm canceling out. So I'm not going to cross anything out. I'm just going to write what you get after you would cancel those out. According to the derivative equals 0 at t equals plus or minus 1. It's undefined at t equals 1. Now something's happening at 1. Now, if there was a theorem that we talked about at some point where if dx dt and dy dt are 0 at the same time, which is what's happening at 1, because you can see the top dx dt is 0 and dy dt is 0, that usually means it's not smooth. So that already told us a lot about this graph. It's not smooth at 1. And another way you can think about that is if you do get that cancellation, there's something going on at 1. It's not going to be a min or a max necessarily, but it's going to be unsmooth. And if we go back to look at the graph, you can clearly see that when t does equal 1, that's right there. You can see up here where b is 1, that's where I put the t. It is an unsmooth graph. Where t equals -1, which is right here, it looks like the derivative is 0. So everything's sort of making sense based off the derivative, which is always a good thing. Now let's get x and y coordinates here. So what I'm thinking here is t equals -1. We have a maximum. I'm only saying it's a maximum. I know the derivative is 0. It's a maximum because I cheated. I looked at the graph. If you look at this, it is a maximum because when before negative 1t is negative, and before t equals negative 1, the derivative is negative. After t equals negative 1, the derivative is positive. So it is a max. We can get the x and y coordinates just by plugging that t into the x and y parts of the parametric equation. So when t equals negative 1, x equals negative 1 squared, 1, minus 2 times negative 1, so 1 plus 2, which is 3. And y, when you plug negative 1, you get negative 1 cubed, which is negative 1, minus 3 times a negative 1, or plus 3, so y equals 2. So that maximum should occur at the x, y coordinates 3, 2. And I'm going to go back and look at the graph just to make sure that looks right. So I'm looking for 3, 2, 1, 2, 3, 1, 2. That looks perfect. Now that place where it's unsmooth, let's figure out what those x and y coordinates are. That's the same thing. We figured out it was unsmooth at t equals 1. Or the derivative is also undefined. So unsmooth, undefined derivative. If you plug in 1 to x up in the upper left-hand corner, you will get x equals 1 minus 2, negative 1. If you plug in t equals 1 to the y, you'll get 1 minus 3, which is equal to negative 2. So that unsmooth point, the undefined derivative, should be at negative 1 comma negative 2 in the coordinate plane, and it, negative 1 comma negative 2, negative 1 comma negative 2, it is. So the calculus behind the parametric equation tells us a lot. We could have some more fun with this, look at the second derivative and find out about the concavity, which it looks like it's concave down and to concave up. That looks like concave up. The second derivative isn't hard to find. You would just take the derivative of this, 3t plus 1 over 2, and put it over 2t minus 1. So that actually is pretty easy. It's 3 over 2 times 2t minus 1. So still, you would have just that possible inflection point at 1. T equals 1, or x equals negative 1, y equals negative 2. You can also look for equations of tangent lines. I'm going to do that, but I'm going to do it in the next video, as this is getting pretty long. So hopefully that was as exciting for you as it was for me.